Welcome to our Artificial Intelligence through Artificial Intelligence YouTube channel and to the Introduction to Deep Learning with PyTorch course. In videos 7 and 8, we saw that sigmoidal activation functions, such as the sigmoid and tanh, are prone to saturation, leading to the vanishing gradient problem in deep neural networks. To build a solid understanding of this issue, we examined several key concepts and related terminologies in videos 9 through 12. This video explains the concept of the vanishing gradient problem in simple terms, without using heavy mathematics, making it easy for anyone to understand. So, let's dive into one of the most important challenges in deep learning. During the forward pass, a neural network receives an input, processes it through its layers, and generates an output. This output is then compared to the target or actual value to calculate the loss, which represents the difference between the predicted and actual values. For instance, consider a simple 3-layer neural network where the input is 0.5, all weights, W1, W2, W3, are initialized to 0.5, all biases are set to 0, and the target output or actual value denoted by Y is 0.8. This target value is also referred to as the ground truth. After the forward pass, the network produces a predicted output of 0.571, denoted by Y hat. Using the mean squared error formula, the loss is calculated as 0.0262. This value indicates that the model's prediction differs significantly from the actual value, suggesting that the model has not yet learned the underlying pattern effectively. To reduce this loss and improve the model's accuracy, a backward pass is performed to update the weights and biases based on the computed gradient. Next, the backward pass is applied, moving from the output layer back toward the input layer in order to minimize the loss. During this process, the neural network updates its weights and biases to improve performance. This optimization is carried out using the chain rule, which enables the computation of gradients for each layer. However, as these gradients are propagated backward, they often diminish in magnitude. When gradients become very small, approaching zero, the weights in the earlier layers receive minimal updates. As a result, the network learns very slowly or not at all in those layers. This issue is known as the vanishing gradient problem. In this scenario, you can observe that W3 is updated significantly, W2 changes only slightly, and W1 is not updated absolutely. This demonstrates that most of the learning occurs in the deeper layers, while the earlier layers experience negligible learning, an effect that clearly illustrates the vanishing gradient problem. That wraps up today's video. If you found this helpful, please don't forget to subscribe, like, share, and comment to stay updated with this series.